Just a couple more applications of the comparison test and we're all done. So let's look at 2 plus cosine of x over the square root of x. Now in this one, they didn't give us the function that they want us to compare it to. So we're going to have to be crafty about it. So if you look at 2 plus the square root of x over, 2 plus cosine of x over the square root of x, it's this wavy curve right here. And so what I noticed to myself is that 2 plus cosine of x, cosine of x, we'll make a big note about this because we'll use this a lot. And remind yourself that the comparison test is not going to go away. It's going to come back in chapter 10, so you might as well be used to it. So the negative 1 is less than or equal to cosine of x, which is less than or equal to 1. Okay, so that helps me out a little bit. And it's also true of sine of x, by the way. Just as a little heads up. Okay, so our curve is 2 plus the cosine of x over the square root of x, right? So I want to come up with something that I can compare it to. Well, why don't I put in negative 1 and 1 for this? So if I put in negative 1, that would be me 2 plus negative 1, which would be 1 over the square root of x. And if I put in positive 1, 2 plus 1 is 3 over the square root of x. And that's true because cosine is between 1 and negative 1. So that will be fine for me, and then this would be the case, right? Okay, well, the one on the left, this one over here, we actually already proved this is divergent. We proved it in a previous example. Let me go find it. Oh, this was a while ago. It's right there. See? Now, it's granted you it's going from 2, but that part's irrelevant. It doesn't really matter what constant you start off with. So we proved that in example 3, in this section, of course, we proved, oh, and I should say we are going from 1 to infinity, sorry. 1 to infinity, 1 to infinity, 1 to infinity. So in example 3 in this section, we proved that the integral of 1 over x to the 1/2 dx is divergent. As a matter of fact, we have a theorem for it. Which was on the next page after that, right? Or maybe it was the previous page. There's a comparison to make. Oh, yep, right here. We called it a fact, but it's true, right? So if p is greater than 1, it's convergent. But if p is less than a half, less than 1, which a half is less than 1, then it's divergent. So also by the fact. It was page, let's see, this semester that I'm teaching it, it is on page 177. I can't guarantee it'll stay that page forever, but that's where you have it now. All right, so divergent, right? So it goes to infinity. And since it's the smaller function, so two things we've proven. We just proved that it's divergent. So if you will, I've got them in reverse order to what I did last time. So I've got the divergency part proved. Up here, I have the less than or equal to part proved. And you can see it actually when I look at it on the graph. So there's the function. Let me graph 1 over the square root of x, and then there's 3 over the square root of x. And you'll see that that function's always between the two. And the important part is that green one, right? That green one is divergent. And since it's divergent, then the purple one that's always above it also has to be divergent. That's the comparison test. Right? From 1 to infinity diverges also. Right? And there's part 3. So step 1's here. I kind of got them in opposite order from the last time. I did the divergence proof, divergence or convergence. Step 2, which I have an opposite, I proved that this function is always less than this function. Since the little one, the smaller one, right here, smaller one diverges, then the bigger one also must diverge. All right, then now let's move on to the next one. Same kind of deal. So I have dx over x to the 1/3 plus x. Okay, so let's think about this. So dx over x to the 1/3 plus x. Well, let's think. If we would think about our fractions, if I make, and I'm doing an integral from 0 to 1, and the problem, by the way, is 0, right? If we put 0 in, it'd be 0 plus 0, which is 0, and that's bad, right? Okay, so let's think here. What do I know? I know that in fractions, if I make the denominator smaller, it makes the overall fraction larger and vice versa, right? So let's think here. Remember that a half is greater than, is greater than, not equal to, greater than a third. Let's make a little note. So if I make my denominator bigger, it will make the overall fraction smaller. Well, how do I make my denominator larger? Let's think here. Well, how about I play with this x and this x? So I could go, let's think here, 0 to 1 dx square root x plus x. And then I can go 0 to 1 dx over x to the 1/3 plus x to the 1/3. Like that. Now let's see if my less than or equal to's are correct. Let's check with Desmos. Right here. Okay, so the original function, let me leave it on, is the purple one right there, right? So it's x to the 1/3 plus x. And let's see if the ones I came up with are indeed less than. So there's x to the 1/3 plus x to the 1/3 right there. And you can see it is smaller. Now, you might be wondering, why is that happening? You made it a smaller number. Yeah, but it's under a square root, so it ended up working out to work out beautifully for me. Oh, and of course, the trick is that we're only looking from 0 to 1. That's the real kick, because when you're only looking from 0 to 1, decimals and fractions to 1/3 powers are actually larger. So it seems kind of crazy, but you've actually, by going to x to 1/3, you actually made it bigger, or smaller, excuse me. The overall function is smaller. Crazy, huh? Right? It works kind of the opposite of what you think it would. And it's because these are all fractions, right? So everything kind of flips up and does weird things. All right, then the other one I thought of was this one, which is that red one right there. Okay, so that red one is going to have problems. It's going to diverge, which doesn't really do me any good, because if the larger one diverges, nothing is known. It's useless to me. Right? So let me kind of prove that. So this one, if I just kind of ponder this one for a second, if I do this one, it's 0 to 1 of 1 over 2 square root of x dx. It's the square root, it diverges. It's by the fact that we know from that previous page. I should number that fact or something. And that's not useful to us, right? So it's a larger function, but it diverges. Larger function diverging doesn't do me any good. All right, boo. Let's go to this side. All right, so on this side, I want this one, it's smaller, I want it to diverge. If it diverges, it will be great. Okay, well, let's look at it. So it's a smaller function. This is x to the 1/3, x to the 1/3, so that's 2, right? Oh, square root of 2 over here. I'm sorry, it was the square root of 2, right? I apologize. Okay, so this one is 2 to the integral 0 to 1 dx over square root 2x to the 1/3, right? That's this one going that way. Oh, I should have written that in a different color. Hold on. There we go. Okay, but again, that is, let's see, write this. This is 0 to 1. It's 1 over the square root of 2, because that constant just come out. Dx over x to the 1/3 to the 1/2, which is 1/6, right? A third to the half. And that diverges, again, by that same fact. And we're going to use that fact all the time. I should go find out what page that was. It was page 177. I already found that, I know, but I forgot. All right, page 177. So we're using that one all over the place, and that will continue to be the case, right? So it diverges. Okay, again, the smaller one is diverging, right? So up here, I did part 2. I proved that one graph was less than the, or one function was less than the other function over this interval. And then I proved that that smaller function diverges. Smaller function diverges. I also proved that the larger function diverges, but the larger function diverging is useless to me. So that's gone. So I proved that the smaller function diverges. These two pieces together, the fact that the original function, original integrand, is always larger than this function and its integrand. This area is always larger than this area. Since this area diverges, that means that this other one must also. So therefore, here's what those 3 dots in a triangle shape mean. It means therefore. The integral from 0 to 1 of dx over x to the 1/3 plus x diverges also. And that was part 3 that I'm showing right there.